As I was telling you, let me check if this is recording. Now I am recording the class. So I was telling you essentially that you use PALU factorization to obtain the L matrix with the coefficients that you use to make all the row operations. In this case, you obtain 1, 0, 3, 1, and then you multiply and obtain the A matrix. Same for the cases of 3 by 3 matrices. You did the same. You eliminate this -3 using the first row times 2, you store it in the second row, then you use the factor -3 times the row number 1 to delete the -3 in the third row, and then store it in here, and then finally you use -7/3 times the second row, which is this one, to eliminate the second element of the third row. So and then you store it in the L matrix. So essentially at the end you obtain the same thing, L times the eliminated, which is the Gaussian elimination matrix, if you think about it, the same thing. And then you just get the A matrix, right? Once again, it was a pretty easy step. So and then we actually use 2 single steps to actually obtain the solution. So you obtain the solution. Essentially, you obtain this matrix LC equal to B, and we solve it for C. L is the L matrix with all the coefficients that we use to obtain the Gaussian elimination. U, in this case, is the matrix that you're going to be using. Well, B is the matrix of the coefficients written by L equal BC. And then you have Ux equal to C, and you have to solve it for X. Once you obtain U, of course, because you need to solve this for U. So essentially, you just multiply the Gaussian elimination matrix, which is this one, for the first step. Was this one multiplied by L, and you obtain this one. So you just multiply this one, you obtain this one. And then finally, you just solve it for B, this one, obtain this one by C. So C is equal to C1 is equal to 3 minus 7. And then once you have this one, you use the Gaussian elimination matrix times X, which is this step, U. And then you equal it to the previous vector, which was actually solved in the first step. And then you solve this equation and obtain the solution that was X equal to 1 and X2 equal to 1 and X1 equal to 2. Same thing you did for the case for 3 by 3. So this is the coefficients, the L matrix that you use. This is U, which is the matrix elimination, and you multiply this one. And then once you have this one, you equal this one to the C coefficients. Well, multiply by C coefficients equally, and you use it to obtain the solution, which is this vector at the very beginning. If you remember this 3, 3, 6, or 3, 3, 3 minus 6, sorry. 3, 3, 3 minus 6, and then you solve for C. After solving for C, you obtain that the solutions are C1 equal to 3, C2 equal to -3, and C3 equal to -4. It was a pretty simple step, actually. You watched the video, and that was actually very well summarized. At the end, solving for X, same thing. You have the C vector, the C vector here. You have the U matrix already solved from the Gaussian elimination. Solving for X, you saw that the solution is equal to 3, 1, and 2. And if you actually use this in the initial system of equations, you will see that you obtain the real solution of the system. So this is another way to solve it, if you think about it. So it's another way. It's pretty similar to what we saw for the Gaussian elimination, but this has some purpose. Why we're using the PALU factorization? So remember that we had 2 conditions to use the Gaussian elimination. First of all, the matrix has to be non-singular, right? Has to be singular matrix. Sorry, non-singular. It means that it has to have a solution. So that's the first step. And then any of the pivot, remember the pivote que tenemos que tomar, has to be what? Greater, or sorry, different than zero. Different than zero. Could be negative, but it has to be different than zero. So that's why we're actually doing this, to go step by step, solving all these things. Then, after that, of course, we saw the applicability of this. This is actually very well applied in structural engineering. And then the limitation. This step requires a little less effort than the Gaussian elimination. So it's the limitation, right? It's like, okay, we're actually recording some steps, so not that good. So another things that we have a limitation, and non-zero pivot is required by the LU factorization, seeing it is based on Gaussian elimination. That's another limitation. But we'll see that this is just something that we're gonna actually solve in the second steps. So not all matrices has LU factorization. That's very important to recognize. Not all the matrices that we are using using LU factorization can be solved. However, this can be actually be solved very easily, and it's gonna be solved in this class. We are going to use the procedure called the PAU or LU factorization. I call it actually, personally, I call it actually PALU Factorization. I call it like that, and it's going to be treated in this class. So you had these exercises. This was the first part of the exercises. They were very easy. That's what I think in general. And you could use, if you think about it, you could use actually the code I already gave you. If you remember in MATLAB, I gave you a code. So if I open MATLAB, essentially, you can use it. Give it a second. It's opening. So let's see. So now that we did actually the summary, I'm gonna start to speaking more slowly because I think I spoke very, very fast. So I will try to make it easier for you to understand because I'm getting exhausted. Sorry, it's still opening. And then we got the MATLAB open. So this is what we got. This in general, you can use this plot, this command, sorry. If you run it, remember that you have to give the matrix, and then you have to give the vector, and then you get, at least for the PALU factorization, you can get actually U, because remember that U is what we got from the what? From this. This is U. The only thing that you need to record, you can actually modify because you just need to get the factors. Remember that the factor is actually the matrix. In this case, the matrix was equal to the, I think this, yeah, it was actually the mult. The mult was actually the multipliers that we use. So if I actually take this mult, for example, I say that these are actually 0.5, 1.5, and 1. Were actually the factors that we multiplied in general. So this was something that we did here. So you just needed to be curious and then just separate this from the others. So for those that were actually doing some more research, if you go to Google, for example, you go to Google and then just use LU factorization MATLAB. You can also have the command actually U factorization. Oh man, accept. Okay, we'll see. So you can get actually the LU factorization. So this is the LU. And then there is another one that is actually equal to the PALU factorization. But you can get from all this, you can get all these factors. So I'm going to show you actually how to do it today. So this is one example. So if you have, I don't know, if you have the matrix A, which is this one, I'm gonna show you this one. So let's just use this matrix, right? So A, I'm gonna close this because I think it's just CLC. So this one is the matrix A. So if I say that I'm going to use, I think it was, sorry, this keyboard is getting complicated for me. It's a new computer, so it's L, U, comma, and then this one equal to LU of A. So there you go. This is what you get, something like this. So you get the L matrix and the U matrix. So this is something that we can get. So this is pretty much, if you think about it, these were actually the coefficients. So let me see, this was one, this one was, I don't remember the results, but in general, I think was 1/3, which is 0.003. And I don't remember this one, but they were the coefficients. So this is what you get, the coefficients, and this is the final version of the matrix actually reduced by Gaussian elimination. So this is for the people that are a little bit curious. You can use it to check your exercises. So, but today we're moving forward to a more complex exercise, just a little bit more complex. So it's not that you're gonna get killed with this one. So this is what we're getting. So today we're, hold on, interpolation. So ground system of equations. Thank God I see them. So this is, we are still in system of equations. So in general, so we are going to see the PA equal to LU factorization. I personally call it PALU factorization. Okay. So from this equation, you already know how to obtain LU, right? You already know how to obtain LU. We just need to get P and we need to get A. Yes. Ya saben cómo obtener ustedes LU, ¿cierto? Kind of. Well, you have to watch the video again then, because that was pretty clear in the video and was in Spanish. So there is no actually excuse to say, Professor, I didn't get your idea because the video was in Spanish. Or probably you need to actually listen to it in English. So you're getting used to my voice in English. But well, it's actually very, very easy. Don't worry. We are going to go step by step in this case. So one of the things that we can say so far about the Gaussian elimination is that Gaussian elimination in general actually could be very naive. When we say naive, it's actually very, how can I say, mathematical expression, ingenuo, no? Because we have two different problems. We have difficulties. So the first of all is the zero pivot. So we cannot actually get a zero pivot. So that's a problem. With that, we have a zero pivot. And we always start from the very top. If you think about it, we're starting down the top. The code was made in the top, and then we start to actually simplify it. And then we have the swamping. So swamping is actually something, swamping. Do you know what is a swamp? What's a swamp?
Un pantano.
Exactly. Swamp es un pantano. So could be actually get very pantanoso. Entonces, so in this case, so swamping means like when we are multiplying by a very, very large number, or a very, very small number, such as something like 1 to the power times to 10 to the power 40, or 1 times 10 to the power 20. So that's a very big number. So for these cases, when we are starting using these numbers, so the resolution or the declaration of our variables in a computer is getting tricky because there are a lot of numbers. Considering that, imagine 1 times to the power 20. ¿Alguien me puede decir en español cuánto es 1 times 10 to the power 20? ¿Cuánto es eso? Dígamelo hablado, por ejemplo, ¿no? Even if we say 10 to the power 20. Or 1 to the power 20, sorry. So how much is that? So can you actually say the number? If I say 1 millón, tengo 1 millón, tengo prácticamente 6 ceros. Si yo digo 1000 millones o 1 billón, es quiere decir que tengo ¿cuántos ceros? Tengo 9 ceros, ¿cierto? Entonces, si yo digo, podría decir a lo mejor, si digo 1 millón de millones, ¿cuánto es 1 millón de millones? Serían, ¿cuántos? 1 millón de millones, ¿cuántos ceros serían?
12, ¿no?
Serían, tengo 6, perdón, y 6, 12. Entonces ya casi llego a la 20, pero ahora sería, ¿y ahora cuánto sería para llegar a 20? ¿Cuántos serían? Si le pongo, ya dije cuánto dije lo último que eran.
No sería.
1000 millones, ¿no? Serían, vamos a decir, 1 billón de billones, ¿cuánto serían? 1 billón de billones.
Ahí ya sería 24, ¿no? 24 ceros.
24 ceros. Entonces,
Pues,
1 billón, exactamente, 1 billón de billones sería 24 ceros, pero es una cifra que no se dice tan fácil, ¿no? Entonces, that kind of situations, actually, you are overpowering a row. When you multiply by this factor, you are overpowering a row. And then you start actually making some things actually confusing for the computer, not for you. Well, actually, if you actually try to do that in your calculator, you can get actually a little bit tricked still, because you are getting only scientific notation. You cannot actually represent it in your calculator. So you only can get scientific notation for that amount of numbers. So that's what we call swamping. Nos volvemos un poco pantanosos, ¿no? Se nos empantana el sistema. So that's swamping in mathematical expression. However, for a singular matrix, both can be avoided with an improved algorithm. So there is something that we just can do to actually improve it. The key to this improvement is an efficient protocol for exchanging rows. So far, we haven't done any exchanging of rows. We haven't exchanged anything, right? We just, move and move and move, just multiply and then subtract, multiply and subtract, multiply and subtract. That's what we have done. We haven't done any exchanging rows. We are not actually sweeping rows. So we always keep the same order. So for this case, we are going to implement a new technique that is called partial pivoting. Okay, that's a new thing that we're going to do, a partial pivoting. So the partial pivoting, so you see that at the start of the classical Gaussian elimination, we have n equations and n unknowns. That's one of the requirements of a linear system. So remember that the first step was to use the diagonal, in this case, the element A11 as a pivot to eliminate the first column. And then we continue to do that several times until we get all the numbers equal to zeros, a lower matrix of zeros, right? So then the partial pivoting protocol in this case consists of comparing the numbers before carrying out each elimination step. What do I mean by this? So we have to compare the position A11, for example, if we're talking about a matrix 3 by 3, we are comparing the A11, the A21, and the A31. So all the elements in the column 1. And we are seeing which one of them are actually the largest number in the column. Okay, so that's why we said that the largest entry of the first column is located, and this row is swapped with the pivot row. Okay, in this case, the top row. So this means, well, this is gonna be clear when we go to the practice. But essentially, we have a column with 2, 4, and 6. So if we start with 2, the first column, we are going to just swap the third row with the first row, and then we move it to the top. Okay. So, however, this is not that easy as you are expecting. So remember that you use these operations when you were doing linear algebra. Esto lo vieron cuando hicieron álgebra lineal, que movían ¿cómo se llama? Filas, ¿no? Solamente lo que hacían es mover las filas, pero no llevaban ustedes ningún registro de cómo es. Ustedes solamente movían y movían también en la matriz de coeficientes para hacerla más fácil, ¿no? Inclusive te recomendaban, no, siempre ponga arriba el 1 y el 1 es el que mata a todos los demás, y luego busca que sea 1, divídete, multiplica por un factor, te vuelve 1 y luego mátalo y así, ¿no? Pero eso mentalmente o manualmente es bueno. Pero recuerden que en métodos numéricos, muchachos, lo que buscamos, aparte de pensar así, como nos dan la clase en español o en álgebra lineal, y nos explican esas técnicas, estamos tratando de reducir ¿qué cosa? ¿Cuál fue lo que vimos al principio? El número de pasos o de steps that we need to actually solve a problem. Why this is so important? Because when you implement this code to have several equations, so this is something that is going to be very useful for you. If you do your code the way you think the way you were taught when you were in algebra, in linear algebra, so it's going to take a lot for the computer to do every single step. So that's why for the computer it's actually easier to implement these cases. And that's why MATLAB actually have these things. Okay, so but we're gonna see one, like step by step. So in other words, at the start of the Gaussian elimination, partial pivoting asks we select the pth row where the AP1, the absolute value, it's greater than the AI1. So we are selecting, in general, the highest value of the column number 1, and you are swapping this value to the first column, sorry, to the first row. Okay, so we'll see this later, don't worry. So that you, for all i's, in this case from 1 to n, which is the number of equation, and exchanges row 1 and p. So that's the things that we're gonna do. We're gonna exchange the row 1 with p, where p is the highest value of the row that we obtain by comparison. Next, the elimination of the column 1 proceed as usual, as you did before in the Gaussian elimination. So using the new version of A11, because this is a new version of the A11 as the pivot, then the multiplier used to eliminate the first column. Remember that it was actually equal to the I to M, was equal to M in the previous classes. Thing is, you've actually think about this in general. I don't see, this one is the M value, this one, these two. So we have it in the Gaussian elimination part, but that's the value. So we have the M value, which is equal to AI1 divided by A11. So in general, if you go to MATLAB and if you open the code, so you'll see that this is the M value, the mult. This is the M value. So essentially, in this case, the MI1 always is going to be what? Less than 1. And if this is less than 1, we avoid what? We avoid overpowering the system. So, con esto nosotros evitamos que se vuelva, ¿qué cosa? Que haya lo que llamamos swamping. Esa es una forma muy implícita de matar ese pajarito de pum, decir, ¿sabes qué? Ya no me puedes dar el error, porque automáticamente cuando yo muevo la primera línea con la primera posición a la primera línea, la cambio, hago un exchange con la primera línea, automáticamente todos los factores m van a ser menores a 1. Y si son menores a 1, pues ya maté 2 pájaros de un tiro, porque ya no van a ser, ya no puede haber swamping, porque todos ya van a estar por debajo de 1. Okay? So the same case is applied to every choice of pivot during the algorithm. Si ya eliminaron, ya tienen la primera columna con ceros y 1 al inicio, o un valor cual sea al inicio, ¿qué hacen? Después nos movemos a la segunda columna, hasta la segunda fila, y ahora la segunda fila tiene que ser, la segunda columna, perdón, todos los miembros de la segunda columna tienen que ser comparados. Y una vez comparados, ¿qué ocurre? Lo que hacemos es hacer si hay otro mayor, hacer el exchanging. Okay? So that's what we have to do. So essentially, we do exactly the same. We actually compare the AP, which is actually the number of the line P, number of the line of the column number 2, has to be greater than the AI2, where AI2 is, if you think about it, is actually all the members I of the second column. So it's pretty simple. So if we actually go to one example later, so if we, for example, go to, let's go on to the more difficult one. So in this case, we start and then eliminate this one and eliminate this one. The new algorithm says that you compare these 3 numbers. Which one is the largest? The absolute value. In absolute value, which one is the greatest, or the largest number? This one, right? This one is actually the -3 is the largest value. So you have to exchange this row with this row. So this one is going to be the new row number 1. Okay? You change it. And then you do the same. You eliminate with this number, you eliminate this column with the zeros like this one, and then you move to the second column, for example, and compare these 2. Which one is the greatest? So is the 7 is the greatest. So you move this one to this position, and then you make this once again. So it's the same thing, but you just have to actually exchange all the rows that we need to do. We're gonna do this in one example, okay? So you do the same thing, and then 8 to 2 is already the largest number. So this is the case that we are trying to do. So no row exchange is made once we obtain the highest value in the second or the third row. The protocol applies to each column during the elimination. So this could be applied for matrices 2 by 2, 3 by 3, 4 by 4, n by n. So the point here is, remember, is eliminating the columns, or making the numbers below the pivot equal to 0 with the largest number in the rows. Okay, so note, as I said, note that using partial pivoting ensures that all multipliers or entries of the L matrix, you already know the L matrix, will not be greater than 1 in absolute value. So that means that we are able to solve the problem of swamping. So let's apply an example, because I think this is better if we actually do an example. So let's start. So we have this equation. This is the simplest one, 2 by 2. 2 by 2, this is the tableau 4, or the tabular form 4. So 1, 1, and 3, 3 minus 4, and 2. So that's clear, right? That's very clear. I think you don't have any doubt about this. Second step. So we start comparing. We compare. We're going to compare this number and this number. Which one is the largest? ¿Cuál es el mayor? ¿1 o 3? Pues 3, ¿verdad? Entonces, el 3, ¿qué hace? El 3 lo que hacemos es, lo pasamos ¿para dónde? Para la primera fila. Hacemos un exchanging. Okay? So we exchange it. If you think about it, actually, it's already changed. And then we multiply the row number 1 by what? By 1/3, and then subtract it to the second row. It's exactly the same what we did before. So we actually say, okay, let's do this. So 1/3, 1 by third, this is equal to 1. 1 minus 1 is equal to what? To 0. So this one is actually minus 4/3, right? 4/3, and then if you want to subtract this one, how much is that? If we have 4/3 subtracted minus my minus, is going to be equal to, in this case, 4 plus 3 is going to be 7/3. And then finally, if we do with this one, so 1/3, and then we multiply by this one is going to be 2/3. And then we have 9/3 minus 2/3 is going to be equal to 7/3. So now we have the elimination. We only have what? 1/3 here, right? So after back substitution, the solution is going to be equal to, if you think about it, this one divided by this one is going to be x1 equal to 2. And then if this is going to be equal to 1, so we just have to actually use this system to obtain the solution, and we obtain that x1 is equal to 2. So you can say it. So if this one is equal to 1, so this one has to be equal to 2 to make the equality valid. So that's very simple, right? It's very, very simple. We just have to change the rows. Actually, you did it when you were in your class. You did it in your linear algebra. However, you didn't see the PALU factorization. So then we solved this system the first time. The multiplier was 3, and then but under partial pivoting, this would be never occur. So si lo hacemos así, estamos de acuerdo, si lo hacemos así directamente, el primer factor sería ¿qué cosa? Directamente sería que 3, ¿no? Multiplico esta por 3 y se lo quito a esto. Así sería la forma más común bajo Gaussian elimination. Pero como utilizamos el factor mayor, all the factors that we are using to reduce this to the triangular, the lower triangular matrix are going to be less than 1. So this value, it's always less than 1. Okay, that's why I said if we do it by as the first time as the Gaussian elimination, the multiplier was equal to or would be equal to 3, but this will never happen under partial pivoting procedure. So that's one of the advantages that we are avoiding overpowering, especially when we do, for example, buildings. When we analyze buildings like huge buildings such as the one that we have the tower here, the 2 towers in the Malecon, in the boulevard. So there are 2 towers. So when you will have a matrix, I would say like you are between, I don't know, like between 3,000 elements. So that would be a matrix of n by n of 3,000 by 3,000. So that would be a lot to solve by hand. So we have to use a computer. And if we have somehow very large values, especially because you have to multiply by the Young modulus and by the inertia of the moment of inertia of each of the elements, so you will have very big values. And when you have very big values, we have the problem of swamping. So this is the problem of just getting limited to what we saw in linear algebra. It's not that easy. So we have to have methods to be able to solve things effectively, because if you get wrong numbers, you get wrong things. You can get a very wrong building and things can get actually very tricky. So you have to be aware of that. Let's practice a second example. Okay, a second example would be a matrix 3 by 3. If you think about it, we never actually do matrix 2 by 4 by 4, 5 by 5, because that's too much for you to do it by hand. Our limit is actually 3 by 3. For the other things, we can use the computer. So I like to be practical. In reality, when you go to work, you will use the computer. So it's a necessary process. So let's just do this. So we have this system. So the first coefficient is equal to 1, -1, 3, and -3. The second is going to be -1, 0, because we have no x2. Then -2 in x3, and then we have 1 in the coefficient, and then we have 2 here, 4, and 0. So what is the first step? Which one is the higher? If we compare the first column, ¿cuál es el valor mayor?
El 2.
2. So we have to swap this. We swap it up, then we swap it up this one, right? So we have the highest number right here. So which one would be the factor? Of course, it would be 1/2 to kill these two. At least the first row is going to be actually guessed. It's going to be -2 because it has to be multiplied -2 and subtracted. Is going to be 0. And then this time, this one still we're going to have 1. And then because this is negative, it's going to be 1. And then this one is 4 divided by 2 is going to be 2. And then this is going to be negative, positive, -2 plus 2 is going to be 0. And then finally, we're going to have this one as the same thing because this is equal to 0. So then we have a 0. Then the second step is going to be actually multiply this one, the first row, by 1/2 again, and then add it to this. Oh, sorry, subtract it to this. So this one is going to be 1, 1 minus 1, 0, 1, and then we have -1, -1, -2, and then we got this one. This one is going to be equal to 2, and then 3 minus 2 is equal to 1, and then this is going to be the same because this is 0. So we killed these two already, and we have two coefficients. We have minus 1/2 and 1/2, right? So now we have to proceed to do this one. So which one is the highest? ¿Cuál es el mayor en esta columna? The -2, right? So -2 has to be moved to where? To this part. So we exchange row 2 and row 3. Ta-da! We did it. So and then we have to multiply -1/2 to get this equal to 0. So multiply this one -2. This is going to be negative, and then 1 minus -1 is going to be 0, and then this one is going to be 1/2, and then 1/2. 1/2. This is equal to 0. Oops, this is equal to 0, so it's going to be 1/2, and then 1/2, or again 1/2, and then this is going to be -1/2. 1 minus, hold on, I just got confused. This is the second row. No, this is going to be 3/2, sorry, 3/2. 3/2, 1/2 plus, sorry, -1 is minus. 3/2 minus 1/2 is going to be equal to -1/2, right? Minus 3/2 plus 1/2 is going to be -1/2. See, yes. So it's fine. So we have this one. So and we already have the Gaussian elimination. Again, we can note that all the three multipliers, this one, and this one, were actually less than 1 in absolute value. So no swamping. We kill swamping. And then if we actually do this, just go back and do the back substitution. We obtain then this is 1, 1 minus 1. If we obtain this one, 1, 1 minus 1, this is going to be 1 minus 1, and this is going to be, what was the last one? -1. This is going to be -3, right? -3, this one is going to be killed with this 2, and then you have -3 and -3. So the solution is already provided. So notice that the partial pivoting solved the problem of 0 pivots. So far so good. Any question? Piece of cake, right? This is actually a piece of cake. Well, just let me drink a little bit of Coke. I got a Coke in the morning, so. It's actually Pepsi. I like Pepsi. If you want to actually give me something, give me a Pepsi Black. I like Pepsi Black. Sorry, everyone has a vice, you know. You drink alcohol, I drink Pepsi. Fair enough. Okay, so before going forward, we have to make another definition. So the second definition is actually the permutation matrices. So the permutation matrices will allow us to actually implement the PALU factorization. Before showing how rows exchanges can be used with the PALU factorization approach, and then of course mix that with the Gaussian elimination, we have to discuss the fundamental properties of the permutation matrix. But we have to define what's a permutation matrix. A permutation matrix is an n times n matrix consisting of all zeros except for a single one in every row and column. So that's a definition. So in general, if you remember, the identity matrix is actually a permutation matrix, right? La matriz de identidad tiene un 1 en la diagonal principal, ¿cierto? Entonces, esa matriz sería como tal una permutation matrix, porque es una matriz que consiste, n por n, que consiste en todos los valores, en todos sus valores son ceros, excepto que tiene un 1 en cada fila. That's a permutation matrix. Equivalently, a permutation matrix P is created by applying arbitrary row exchanges to the n by n identity matrix. Or in this case, we are just making arbitrary column exchanges. So I'm going to give you more example about these things. For example, this is an identity matrix, right? This is a unit or an identity matrix. So if I actually change this row with this row, I get this one, right? I get this one. So this is an example of a permutation matrix. And then for a permutation matrix bigger than this one, than 2 by 2, so we have this one. You have the identity matrix. So what to make this one, I exchange this one with this one, swap it, right? And then if I want to get this one, so I swap this one with this one, and I get this one. If I want to get this one, of course, I swapped all this one to here, this one stay here, and this one goes to here, and I got this one. I want to get this one goes to here, this one goes to here, of course, and this one goes to here. So we get this one. And of course, this one is pretty easy to get. I send this one up, and of course, I send this one up, and this one stays on the bottom. So if you think about it, everything starts from From a identity matrix. Todo inicia de una matriz de identidad. Y de ahí lo que hacemos es jugar con las filas. Lo que estuvimos haciendo previamente. And that's how we actually, if you go to the title again, so the permutation matrix, it's the P. Is the P of the PA equal to UL factorization method. So we need a P for the permutation, and then an A, which is equal to what? To the matrix, the initial matrix, and this is going to be equal to UL, which you already know how to get it. So that's something very nice. So the next theorem that we are going to just define in a second tell us at a glance, just in a very single pick of view, what action a permutation matrix causes when multiplied on the left of another matrix. So pay attention to this, because this is a very important step in this procedure, in the PA equal to UL method. The fundamental theorem of permutation matrix, let P be the n by n permutation matrix. Which one? Any of this. Any of this one. Okay? Form this matrix formed by a particular set of row exchanges applied to the identity matrix. This is what we already had. Then for any matrix for n by n A, P times A is the matrix obtained by applying exactly the same set of row exchanges to A. This is like a professor, I didn't get anything you said. You know, this is difficult. It's it's difficult in Spanish, so in English is even more difficult. So once again, for any n by n matrix A is equal to this matrix. This one A. Remember the A is only this one. A. This is the one. Okay. For any matrix n by n, P equal to A, P times A or PA is the matrix obtained by applying exactly the same set of row operations. ¿Qué quiere decir? Si yo tengo una matriz P que fue cambiado prácticamente, las unidades fueron, las columnas fueron movidas, perdón, las filas fueron movidas, si yo lo multiplico a su izquierda, bueno, a su derecha en este caso, me va a hacer sobre la matriz A las mismas cambios mismos cambios de filas que como yo tuve en la permutación de la matriz. Eso es lo que está diciendo. ¿Ok? For example, so imagine you have this permutation matrix. ¿Cómo obtuvimos esta permutación? ¿Quién me dice? ¿Cómo la obtuvimos? Esto es muy fácil, ¿no? Hice un intercambio de qué filas. De la 2, ¿con cuál? Con la 3. Piece of cake. Thank you, Quiroz Montoya. So that was a piece of cake. So now, easy peasy. So imagine we have a matrix A, and this is actually, there are letters, just to say that it could be any number. Tenemos que A, B, C, D, F, G, H, I, en orden. Si yo multiplico la permutation matrix a su izquierda, ¿qué pasa? Yo la multiplico y obtengo ABC, esta queda igualita. Pero ahora, ¿qué pasó? Ahora GHI, DF, es como si estuvieran, ¿qué cosa? Intercambiadas. O sea, si yo multiplico una matriz permutación de este tipo por una matriz A cuadrada, me está haciendo las mismas operaciones de intercambio que tiene esta matriz. ¿Sí o no? So that's piece of cake. And that's something that we're going to need a lot. ¿Quedó claro o les pongo un ejemplo en MATLAB? Everything is clear? Okay. So there is a good way to remember this. So because the theorem is kind of tricky, so there's just one way to say it. So if I multiply P times by the identity, this is the identity matrix. If I multiply a permutation matrix times the what? The identity matrix, I'm going to get what? This matrix. You see? If I multiply this one times this, the identity matrix, we're going to get always the permutation matrix. Okay? So there are two different ways to view this equality. The first one as the multiplication by the identity matrix. So we get the permutation matrix on the right. Or the second view is as the permutation matrix acting on the rows of the identity matrix. We are more concerned about this, the second one. We want to see the effect of the permutation matrix on the rows, not only the identity matrix, but on the rows on the any matrix. Okay, so that's what we need to do. So now we start to the method. So we go to the PA equal to ALU factorization. Now that we have everything ready, so we go to this term. So P is what? P is the permutation matrix, right? A is equal to what? To the tableau form of the matrix. Square, this is a square matrix, remember? L is equal to what? To the operations recorded. And U is equal to what? To the Gaussian elimination matrix. So this is the matrix formulation of the elimination with partial pivoting. So the PA equal to LU factorization is established workforce for solving systems of linear equation. I would say this without any mistake. This is the best method to solve a system of linear equations. This is the best method to solve a system of linear equations, as long as they are non-singular matrices. When we go to non-singular, we have to go to another type of procedures, but approximation procedures. But when we have singular matrices, this is the best method to solve the system. The best one. Okay. Of course, implying that the PALU factorization in my case is equal to the P equal to LU factorization implies that the LU factorization of a row exchange version of A. That's why, because you did all LU with all this changing that we already saw in the previous exercises like this one. So we have to record all these changes. We have to record everything. So one way to record this, of course, is actually by the permutation matrix. That's why I want to record all the changes. So that's why we need to record, okay, the matrix. And that's why we're going to use the P matrix. To keep track of the previous multipliers, we have the L matrix as we did it before. So let's start with example 1. The example 1, we have the A matrix, remember? So if you think about it, if you go to the first example, so this is the example that we did, no, this one, I think it was example in the first class. In general, it was example of the first class, yes, but we have this one. So we have the A matrix. So the A matrix is this one, and then you have, of course, the vector of the solutions, right? So the first step is to compare the columns. Comparamos la columna número 1? ¿Cuál es el número mayor?
El 4.
Exacto, el 4. Entonces, ¿qué necesito hacer? Necesito llevarme el 4 acá arriba. Tengo que hacer un exchange de la fila 1 con la fila 2, ¿cierto? Entonces, ¿qué hago? Sí. Inicio con esto y lo que hago es que mi matriz de permutación va a llevar todo lo que estoy haciendo. Va a llevar el track. O sea, I'm actually tracking all the changes. Si aquí yo cambié la segunda con la primera, la matriz de permutación también. Inicio de la matriz identidad y cambio la primera con la segunda. Y esta es mi matriz de permutación en este caso. Y quedamos así. Hasta aquí todo entendido, ¿verdad? ¿Cierto?
Sí.
Sí, profe.
Okay, so we have everything we need to start the P matrix. So we already have this tracking. So we start to actually make this zeros. We have to make this 2 zeros. So to make these 2 zeros, of course, what do we have to do? Eso lo van a hacer ustedes en una hoja blanca. ¿Por qué factor tenemos que multiplicar para que eliminar el 2? Háganlo ustedes. ¿Por qué factor?
Por un menos un medio, ¿no?
Por menos un medio. Bueno, por un medio y luego se lo sustraemos a la segunda, ¿no?
Ujú.
Entonces, el primero es por un medio y se lo quitamos. ¿Cómo queda la matriz? ¿Cómo quedaría la matriz? Ahí no tengo los resultados. Yo quiero que ustedes lo hagan aparte. Déjenme, voy a encontrar mi lapicero. ¿Cómo quedaría la matriz? Recuerden, estamos partiendo de esta matriz que es 4, 4, menos 4, 2, 1, 5, 1, 3 y 1. Y queremos eliminar o queremos hacer cero la columna, el A1, el A12 y perdón, el A21 y el A31. Entonces dice, compañero, ¿sabes qué? Pues el primer factor sería un medio y se lo quitamos al segundo. Entonces, ¿cómo me quedaría? Me quedaría 4, 4, menos 4. De ahí me quedaría, por supuesto, 0. Entonces, un medio por el otro sería por un cuarto, sería práctica por un medio por 4 sería 2. Y sería 1 menos 2 sería menos 1. Y el otro quedaría igual en 2. Se lo sustraemos y queda igual a 7. Entonces, la matriz me quedaría 4, 4 menos 4, 0 menos 1, 7, 1, 3 y 1, ¿cierto? ¿Sí o no? Vayan haciendo ustedes, ¿eh? Es esencial que lo vayan haciendo ustedes. ¿Ya les quedó? Como les dije.
Como había dicho, profe.
Acuérdense que tengo que eliminar. Ya hice mi primer exchange. I did my first exchange. I exchanged row 1 with 2. Así este era original. Lo pasé esta fila para acá y esta fila para acá. Y grabé mi permutación. Esta es mi permutación. Ahora, para eliminar el 2 y el 1, primero tengo que multiplicar porque tú me dijiste esta por un medio y sustraérsela a esto. Y tengo que multiplicar esta por ¿cuánto? Por un cuarto y sustraérsela a esta. ¿Cierto? Entonces, si la multiplico por un medio, me va a quedar un medio por un medio por 4, me queda igual a ¿qué? A 2. Y 2 menos 2 te queda igual a 0. Ahora, un medio por un medio por 4 es igual a 2 otra vez, menos 1, perdón, 1 menos 2 te queda menos 1. Y por último, menos 4 por un medio te queda menos 2. 5 menos menos 2 te queda igual a 7. Entonces, la matriz te queda 4, 4, menos 4, 0, menos 1, 7, 1, 3 y 1, que es esta matriz. Pero te queda un 0 aquí. Aquí es un 0. ¿Cierto?
Sí, profe.
Ok, cierto. Ahora, esto es un 0, ¿eh? Lo que yo estoy haciendo es que coloco un círculo y le pongo un medio para llevar también registro de los factores que estoy utilizando. De tal forma que al final, todos estos números que están en mi círculo son ceros. ¿Ok? Recuerda, todos estos números que están en mi círculo son ceros. Pero en este caso yo lo que estoy haciendo es que este círculo me está sirviendo para grabar mi factor, el que estoy multiplicando para eliminarlo. ¿Ok? Bueno, ahora, if I want to eliminate actually this number, I have to multiply this matrix by what? By 1, 4, this row by 1, 4, and then subtract it to this one. Si lo multiplico la primera por un cuarto y se la quito a la tercera, es el primer, bueno, ese es muy fácil porque te queda en este primero te queda 1. 1 menos 1 te queda 0. 0 en esta posición. De ahí te queda 1 igual y sería 2 menos 2, 3 menos 3 menos 3 menos o 2. No, 3 menos 1, perdón, te queda igual a 2. Y por último es menos 1 y 2 menos 1 sería 2 menos, perdón, 2 menos menos 1. Perdón,
Sería
1
3.
menos 1, perdón. Perdón, es estoy confundido.
A uno le quita menos menos 1, ¿no?
Exacto,
Entonces, el menos
queda
por menos
2.
es más,
Entonces
queda
queda
2.
2.
Exacto. Ahí está. Entonces queda esta matriz, pero estos dos son ceros. ¿Cierto?
Correcto, profe.
Entonces, prácticamente yo lo que estoy haciendo es solamente utilizando mis ceros como se llaman placeholders.
Profe,
Okay. Yep.
entonces en la siguiente operación, en la matriz que tenemos aquí a la derecha, hacemos lo mismo de comparar entre la fila 2 y la fila 3. En
Exacto,
los números del medio,
2.
¿cuáles son los mayores, no? Entonces
Exacto.
yo subiría el 2 y bajaría el 1.
Así es. Entonces, mira,
Okay.
si nos vamos a la siguiente, boom. Ahora, subo, ¿ya viste? Subí el 2 que tenía acá, lo subí. ¡Pum! También subí mis factores, ¿se dieron cuenta? Subí todo. Subí todo también mi factor. Entonces subí mi factor y me queda el 2 arriba y el menos 1. ¿Y qué hice? De la primera matriz de permutación que tenía, tú me dijiste que cambio este, lo bajo para acá, ¿no? Y entonces también la matriz de permutación, estoy pasando este para acá. También hago el cambio en la matriz de permutación. Paso el 1 a este y baja el menos 1. Y entonces la matriz de permutación también baja. ¿Sí logras ver este cambio? También en la matriz de permutación. ¿Sí quedó claro esa parte?
Sí, profe, sí.
Okay, so now what we need to do to eliminate this one, we have to multiply this row by minus 1/2 and then make this equal to 0. So let's do it. So this one is minus 1/2. In this case, it's going to be times this one is going to be 1 minus 1, sorry, minus 1 plus 1 is going to be equal to 0. And then this is going to be minus, this is going to be 7/2, right? No, minus 7/2. Minus, this is going to be equal to 1, sorry, 1. And then 7 minus 1 is going to be 8. So this is the value. So, and then this is 0, 0, and 0. But we are storing the factors. ¿Hasta ahí alguna pregunta?
No, profe,
No,
pues ya
profe.
nos dijo que los que están encerrados, pues son ceros, ya con eso me ubiqué.
Exactly.
Sí.
So
Es conveniente trabajar los números que se van a eliminar con sus, ¿cómo decirlo? Con sus valores positivos o negativos. Hace rato el compañero Montoya le había comentado que había un número que le íbamos a multiplicar por o sea, creo que era menos 2 o algo así, no me acuerdo, en una operación anterior. Usted dijo que no, que fuera el positivo. El un medio. Entonces usted me está dando cuenta que en el otro también el número que queremos eliminar es negativo y la fila que de arriba, que es la 2, la multiplicamos por un número negativo. Entonces,
sí, pero acuérdense que siempre estamos sustrayendo. Siempre hay una...
se quita. Es sustracción la operación. Ok, perfecto.
Siempre estamos sustrayendo. Recuerden que es una sustracción. Nunca estamos sumando. Siempre sustraemos.
Ok.
Okay?
Ya. No,
So,
eso.
now we have the LU. This is actually the LU. All the LU, if you think about it. ¿Por qué? Porque tenemos L, que en este caso sería todos estos unos con este caso con 0, 0, 0, digo, por un cuarto, menos un cuarto, 0, 0, 0. Y tenemos el U, que sería 4, 4, menos 4, 2, 2, 8, 0, 0, 0. Entonces tenemos todas las matrices. Entonces si nos damos cuenta, aquí está, miren, LU es la matriz identidad con los factores que están en circulitos. L. Right? U is the Gaussian elimination. 4, 4 minus 4, 2, 2, 8, 0, and then 0, 0, sorry, 8, 0, 0, 0. This is U. And then we have the P, which is the last permutation, P, that is affecting the A matrix. Which one is the A matrix? The original one, this one. The original matrix. So that's the shape of the PA equal to LU method. So do you have any question how I arrived to this point? ¿Alguna pregunta?
Ya vi por qué el PALU.
Exactly, PALU factorization. So remember, we have to keep track of the changes of the rows by the permutation matrix. And we have to keep track of the what? Of the factors with the L matrix. So, and then we for the PALU procedure. Okay? So if you think about it, this is actually a very small variation of the LU factorization. Okay, so now what do we have to do? The same steps. So now we have the PAX equal to PB, and then the LUX equal to PV. So in general, we have to solve this. This is the general form of the equation, remember. But what we have to do to solve the system is equal to L is equal to C equal to P times B. And we have to solve for C. And then U times X equal to C, which is obtained for this one, and we solve for X. Okay? That's the way we're going to solve it. Okay? So the important point here is, as mentioned, I mentioned earlier, is that the expressive part of the calculation determining the PALU factorization can be done without knowing B. Recuerden que aquí no tenemos que saber, aquí ya no nos importó este caso cuánto valían los coeficientes que estaban aquí al igual. Recuerden que en la forma de tabla, que es esta, aquí teníamos que tener este valor y teníamos que aplicar todas las operaciones a todos, inclusive a los coeficientes. Aquí ya no, aquí no tenemos que aplicarlos. ¿Por qué no tenemos que aplicarlos? Porque para eso estamos haciendo la matriz P. Miren, P es las permutaciones. Entonces, si multiplico B por P, ya tengo yo las permutaciones que hice con mis valores. Entonces, no tiene caso que yo las haga. ¿Ok? Entonces, eso es lo importante. So, then we have to do the examples. Para el ejemplo 2 que hicimos, recuerden que es este ejemplo. Bueno, el ejemplo 1 que hicimos. Ahora le añadimos sus soluciones. Esto es igual a x1, 2x1 más x2 más 5x igual a 5. Esto igual es 4x1 más 4x2 menos 4x3 igual a 0. Y este es igual a x menos 3, x1, perdón, menos 3x2 más x1 igual a 6. So it's the same thing. So now we can actually do the procedure. So we already know that L comes from here. L is the matrix with all the factors. We multiply this one times the C, which is the one that we're looking for, and then we have the P, the permutation matrix, and B, which is the value of this one. If you multiply this one by this one, you obtain 0, 6, and 5. And then we just solve for C. Solving for C, in this case, if you have this one solving for C, you can see that if you go backwards, C is going to be equal to 0. And then we have that if C1 is equal to 0, this one C2 is going to be equal to 6. And then if you do this operation once again, because this you have 6 here, of course it's equal to 6. And then if this is 0, and then you have 1/2, and then you have 5, so this is going to be equal to 8. Z3, because you have here negative numbers, so you just have to add 5 plus 3 is going to be equal to 8, because you are dividing 6 divided by 2, and this is equal to 0, you have 8. So now we have the C vector. The C vector is equal to 0, 6, 8. And the last step is going to be equal to, of course, the U. Which one is U? U is this one. And then if U is this one, you already have this one. And then you multiply it by B. And then sorry, not this one. You multiply this one, U, and then you have X, and then you have C, which is the vector that we obtained. And then you solve for X. So you see that this is going to be X3 is going to be equal to 1. Because A divided by A is going to be equal to 1. Then if this is equal to 1, this is going to be 2 plus 2. 6 divided by, in this case, is 6. 2 plus 2, in this case, you have 2 divided by, no, sorry. This is going to be negative, it's going to be 4, and then 2 divided by 2, 4 divided by 2 is going to be 2. And then finally, you know that this is 2, this is 4, and then you have 4, 8, and then this is minus 4 is going to be equal to 4. Is going to be equal to 0, sorry, no, to 4, and then 4 divided by, minus 4 divided by 4 is equal to minus 1. So you got the solution, 1, 2, and minus 1. Okay, so do you have any question about how I did this? ¿Alguna pregunta?
No, profe.
It's pretty simple. It's pretty similar to the one, but the one that we need, the things that we need to actually get is this one. Once we have this one, we are done, because this is just following the example 1, the step 1, which is this one, and the step number 2, which is this one. We obtain the solution directly 0, 6, 8, and then you get 1, 2, minus 1. Si nosotros tenemos que esto es 1, 2 y menos 1, si vamos al original, que es este, sería 2, aquí sería 2, luego sería más 2, menos 5, sería igual en este caso igual a 5. Si tengo 2 menos 2, sería en este caso, se va y queda igual a 5. Entonces sí hay equivalencia en este caso de la solución. Entonces sí existe la solución, lo mismo para ese, si lo queremos hacer, es exactamente lo mismo. ¿Ok? ¿Qué sería? Este sería, si este es menos 1, sería este es 4, 4, este es 2, sería 8, y aquí sería menos 4 por menos 1, sería 4, y 4 son 8, menos 8 da 0. Entonces también se cumple. Esto es lo que hace en este caso la PALU Factorization, alias PALU Factorization for me. Okay, so this is the procedure, and these are the what happened? This is the second set of exercises. Ya tenían uno ustedes, que ya se supone que ya los hicieron. Ahora van a hacer estos, y ahora sí yo voy a publicar la actividad donde van a incluir tanto los LU Factorization como los PAL Factorization method. Okay, so this is the one, and no los voy a dejar a ciegas. No los voy a dejar a ciegas porque les voy a ayudar con un poco. A ver. A ver, uy, esto no es. A ver, ¿dónde está? Okay, give me a second. MATLAB, what's the MATLAB? Here. So I'm going to give you an example of how to do this in MATLAB, okay? Because it's important for you to have something to verify. Lo que me gusta es que quiero dejarles algo para que ustedes puedan verificar, ¿no? Porque si no luego pues no pueden verificar y todo pues apesta, ¿no? Porque me gusta que ustedes saquen calificaciones aprobatorias. No es el chiste que los reviente, ¿no? So you saw, for example, if we have the A matrix, the A matrix in the example was equal to this one. Let's go to the example. This is the factorization. Let me just go to the no. This is a PowerPoint. So PowerPoint, the example was equal to 215. I'm going to actually put it right here to be able to copy. So you have 215. 215, 4 minus 4 is 4, right? And then we had 1, 3, 1. So this is the example that we already did This is the example. See, this is the example. Okay. So now that we have the example, we can actually go and do it in MATLAB. So remember that I told you that the LU, if you compute the LU para los ejercicios, sorry. You have the L comma U, and you have the LU, and then you have the matrix A. This is the matrix. So if you actually compare this one with what we got, espero que no me quede mal. So this one was the things that we got, right? This one. So we got the LU. Well, this is the LU factorization. It's going to be a little bit different. But, well, we got the LU, but it's an equivalent matrix. Okay, but let's just use the same example, but just add the P here. There you go. So now, if you check this out, so you got the permutation matrix is equal to this one, right? You see that this is a permutation matrix. 0, 1, 0, 0, 0, 1, 1, 0, 0. And then, oh, I made a mistake here. That's why it's not actually, hold on, I have a mistake. Didn't see that. I said, why is not the same? But now I see why it's not the same. So now they are the same. I had a mistake. So it's equal to the original matrix is equal to 2, 1, 5, 4, 4 minus 4, 1, 3, 1. So now it makes sense. So now if we use LU, you see that this is L and this is U. So for the two methods, L and U, you see here is actually L. It's, well, this is 0.051. But if you think about it, it's the same because you actually swap this up to here is 101, 101, and then 1/4, 1 and 0, and then 0.5 minus 0.5 and 1, 0.5 minus 0.5 and 1 is the same thing. And then the U matrix is 4, 4 minus 4, and then 0, 2, 2, and 0, 0, 8. And then if we apply the PALU factorization, we just have to add this P, and then you obtain P, which is equal to this one. A, you already know A, which is A is this one. L is equal to this matrix. You see that this is equal to this 1, 0, 1, 1 quarter, 1, 0, and half minus 1 half 1. And then U, of course, is the same thing. So this is a way to actually, this is not the way you're going to do it. I'm just giving you a tool to actually be able to compare your answers that you're going to do by hand. Okay. Les estoy dando una herramienta para que tengan y que saquen 10 de calificación. Si no sacan 10 con la herramienta que estoy dando de MATLAB, métanse un tiro. Porque deberían de sacar 10 en esta tarea, ¿no? ¿Ok? ¿Preguntas? Hello? Are you there?
No, profe.
No, ¿sin preguntas?
Todo bien, todo bien.
Okay, perfect. So then just please continue with the exercises at home. And this is it for today, guys. So this is the end of the class. And if you have more questions, of course, you can also review rewatch the video, because the video is going to be available for you. Or you can text me in WhatsApp or somewhere else. Okay?
Profe.
Yes.
Lo que pasa es que yo el martes no pude entrar. Bueno, de hecho le escribí un correo, no sé si lo pudo leer.
Yes,
el caso es que yo no tengo acceso al video de la clase del martes, entonces no sé si me pudiera proporcionar el link o...
It's in my YouTube channel. You can actually watch in the YouTube channel. It's actually it's called UL Factorization. PALU Factorization.
Ok, en el canal de YouTube.
Yes, there is a video. It's in Spanish.
Ok, ahorita lo busco. Muchas gracias.
No problem. You're very welcome. So you have more questions?
Del martes había dejado actividad.
Yeah, the exercises are still are also in the same video. So
en el video están los ejercicios.
Exactly, but I'm going to actually upload these two slides to actually for you to have this second section of the exercises. Estos dos, tanto el de LU y el de PALU Factorization, van a ir juntos. Esa va a ser un solo ejercicio, ¿ok? Es una sola tarea.
Ok, entonces los del martes y los de hoy son una sola tarea.
Así es, y la van a ver publicada el día de hoy por la tarde.
Ok, gracias.
You're very welcome. More questions?
Profe.
Ninguna, profe.
Okay, thank you very much for coming, and I'll see you next class. Have an excellent day, have an excellent weekend, and enjoy yourself. Bye-bye.
Igualmente, profe, hasta luego.
Peace.
Hasta luego, profe.
Chao.